overflowing the stack, so to speak. So let's see if this thing now works. Let me go to sigma 2, make sigma 2. Seems to compile OK. Let me do sigma 2, enter. And now let me go ahead and do positive integer. Let's give it 2. So that works. Let's give it 3. That works. Let's give it 10. Seems to be working. Let's give it a bigger number. Seems to be working. Let's give it an even bigger number. OK, interesting. So just because we have a base case doesn't mean the solution is perfect, right? Even apparently calling, this is what, 1 million times, calling the same function a million times is apparently bad. But that's OK, because this technique of recursion is still something we can leverage to solve, say, the problem of sorting. Because especially with sorting, even if there are a million elements, the goal of doing divide and conquer, recall, is to whittle these problems down to something much smaller, much fewer steps than anything linear with n. So let's go ahead and take a quick break. But when we come back, we'll now apply this idea to the solving of sorting. All right. So before class, I borrowed a few milk cartons from Annenberg across the way to see if we can't take a human approach to sorting these elements while still executing these relatively straightforward instructions. And let's see if we can't understand why and how merge sort is actually speeding ahead so much more effectively than bubble or selection sort. For this, we need just one volunteer. Someone perhaps who hasn't been up here before to kind of run the show with these 8 milk cartons. Come on down. All right, so let's see how well this works. The algorithm itself is correct, so let's see if we can now do it some justice. What's your name? Joseph. OK, good to meet you. Come on up. David. All right, so here are the same exact numbers in the same exact order as last week. And for logistical purposes, you want to hop back down on the ground floor there. And the goal is going to be to sort these things. But thankfully, this time, we have some written instructions. So the input here now is of size 8. So first, I'm going to ask the question, is 8 less than 2? OK, so no, it's not, obviously. So we proceed with the else. So else, I say, sort left half of elements. So left half looks like these 4 here. So now if you interpret the same algorithm, how are you going to sort the left half of these elements?
I'm going to cut them in half and do it again.
OK, so he's going to cut them in half and do it again. And just hold it a little closer there. So OK, so cut it in half. Why cut in half? Well, Joseph needs an algorithm with which to sort the left half. The only algorithms we have are bubble sort, selection sort. Today, those are disqualified. It's way too slow. So we only have merge sort. So let's do the same thing. So here is now a list of size 4. So is 4 less than 2? No. No. So now we sort the left half of elements. So you hand me this. What do you do?
N is not less than 2.
Not less than 2, because it is 2.
We cut it in half again.
So we cut it in half again. So now here's a list of size 1. Is 1 less than 2?
Yeah.
OK, obviously it is. And so what do you do?
Return. OK,
so this is sorted, right? This is progress now. The left half of the left half of the left half is now sorted, even though Joseph literally didn't need to lift a finger. So what step comes next? Where are we in the story?
We merge.
Oh, careful.
We're at the else.
We're still in the else.
Turn, and then we call again.
Good. So we sorted the left half, but what comes after sort left half?
We sort the right half.
So now we sort the right half. Here's the right half. On input n equals 1. Is 1 less than 2?
Yeah.
It is. So he returns. This is great. Now we have 2 bytes of the problem solved. So now what's the next step?
We merge them.
OK, so we merge them. So now you can finally do something. OK. So good. This is actually pretty good progress. We've sorted this part of the list. Now, they're not necessarily in perfect order, because 2 probably shouldn't be all the way at the end, because there is a 1. 4 shouldn't be there, but at least this is progress. So now mentally, we kind of have to start rewinding. How did we get to the point of merging these 2 halves? Well, we started here because this is the right half of the input of size 4. Right? So you kind of have to mentally recurse in backwards to where we started. So here's input of 4. You just sorted the left half. What comes next? All right, so let's sort the right half. How do we sort the right half?
Cut it in half again.
OK, here's the left half.
Return 6.
Here's the right half.
Return 8.
Here's both of them together.
Beautiful.
OK, merged. They're already merged. All right, so that's good. It's really minimal work so far. So where are we in the story?
Now we have to merge the 2 halves together again.
Perfect, because now, if you again rewind mentally, we've sorted the left half. We just sorted the right half. So what comes next? Merge the sorted halves. Now it's a little more interesting. So go ahead and implement this idea of merging.
Well.
Good. Very well done. So 2, 4, 6, 8. So we're done. Hopefully the right side is going to be more interesting. So where are we now in the story? We've hit the bottom of that else condition. This was the left half of the input of size
8.
All right. So why don't we put you on autopilot now? And do you want to tell us, though, verbally what you're doing?
Okay, so now we're on the right half of the input of size 8. So we cut that in half and look at the left half. And then we cut that in half and look at the left half of that. Return 1, return 3 for the right half, and those are already merged. So then we come over here and we cut this half in half and return 7, return 5, and then merge these. Beautiful.
Very well done.
And now we have to merge the whole half with the whole half.
Good. Both halves of size 4. So now how do we do this? And this part, so clearly the real work is involved in the merging, right? Again, hence the name merge sort. So be a little precise now verbally. How are you going to merge these two?
Okay, well.
And just to be clear, there's one half, there's the other.
Okay, so I assume you look at the left end of this half, and the left end of that half and compare them.
Okay, so comparison, another theme thus far.
And so if that entity is smaller than that entity, you move it and you merge those two first.
Okay, so good. So it turns out here's one point worth making. So we kind of need some extra space now, right? Because if we kind of take last week's approach of just swapping these guys, then we're screwing up all the work we just did. It is a good thing that 2 is on the left over here. It's a good thing that 1 is on the left of the right half. So we can't just kind of arbitrarily swap 2 people and say, we'll fix that later. Because if we fix that later, this supposedly fast merge sort algorithm is going to start taking even more time. So it turns out that one of the hidden costs of merge sort and one of the key ingredients to making it so fast in those visualizations is that Joseph actually needs extra space. So it was actually deliberate that I left a foot or so of space here in front of these buckets because merge sort gains its efficiency. It decreases its time by increasing its space requirement, its memory requirement. So put more technically, for merge sort, you need 2 arrays. One empty, one is the original array, and you use the empty one to put the elements into by the end. So now you have as much memory as you want, 8 new spots, so where are you going to put 1? Okay, so 1 goes there. And actually, let's put them in different places, so separate arrays, but we can still let it peek through. Okay, so now what happens next? 1 was less than 2, so 1 goes into the leftmost location of the new array. What do you want to do next?
So then would you still compare the left, this array with the next element? And
Perfect. So you repeat. So you look at the left end of the left half, the left end of the right half, compare those 2 values. Turns out 2 is in fact smaller, so where does 2 go?
Right there.
Right there, and so let's put it into the new memory space. All right, so now what are you going to compare?
The left end of this and the left end of that.
So 4 versus 3?
And 3 is smaller.
Okay. So even though this kind of feels like there's a lot of work going on here, notice one key takeaway. Every time Joseph puts a number into the new array, he never has to go back, right? There's no looping back and forth like Casey had to do last week. Moreover, he's only looking at each of these, he's only moving to the left of these elements once. As soon as he considers an element and decides it's smaller, that's it. It's out of rotation. So how many elements in total do we have to merge?
8.
8, right? Or really 7, because the last one we get for free. So n or n minus 1. So that 2 is key here. The number of elements we need to merge is maximally n, because we have n empty spots. We have n buckets. We need to put them into the empty spots. All right, so where are we in the story? Comparing what?
So now we're comparing 4 and 5.
4 and 5.
4 goes.
Okay. Now we're comparing.
6 and 5.
Okay.
5 goes here.
Now we're comparing.
6 and 7. And
Okay.
6 goes here. And then 8 and 7. Put 7 here. And then 8 goes right.
Done. Okay. A big round of applause if we could for Joseph. Well done. So as is always the case with these human demos, feels like that took a while, right? It really did take some time. But think about how much time if we try to express it in those n terms that we did last week. So every time, the way we started this algorithm is we divided the list in half. And then we divided the list in half. And then we divided the list in half. Well, this is kind of an easy answer now to this part of the question. How many times can you divide n things in half? Formulaically. So that's log n, right? It's technically log base 2n. And even if you're a little hazy on what logarithms are for now, just know that anytime we ask the question, how many times can you divide something in half? Well, it's going to be log base 2 of the something. Or really, we, again, just like last week, we said, divide by 2 plus 2, who cares? Let's ignore constant factors. Same deal with logarithms. So we'll almost always just say log n. So log n is what gives us that nice shaped curve that was not straight, but rather curved. And that's what gave us that added performance boost. So there's definitely something log n involved here. So a quick sanity check. Can you sort n elements in log n time? Right, is that the answer? It's actually not. But why does it take more than log n steps to sort n elements? OK, so that's actually the full answer. But just logically, if I've got n elements and I claim I can sort these in log n steps, you can immediately say, not possible, even if you have no idea how I'm claiming to do it. Because what? In order to sort n elements, you kind of just logically, minimally need to do what with each of them? At least like look at it, right? You at least have to check, is it in the right place? So just logically, if you need to solve the problem that involves sorting n elements, minimally, the lower bound is going to be n steps. Because if it's any less than that, you're just guessing. You're just claiming sorted when you haven't even looked at all of those elements. So again, here too is kind of a mental rule of thumb. You can decide, that's not realistic because you can't possibly sort all n elements in less than n steps. Because again, you need to look at each of them. Now, quick sanity check. When we had Sean on video up at the board here, he was able to find an element in log n steps. But that was OK. When Sean was looking for the number 7, he didn't have to look at all of the other elements, right? When they were sorted, rather, Sean was doing it randomly. But when we then did it ourselves up on stage, we sorted the elements in advance. And so you don't need to look at all of the elements if you already know, those are smaller than what I'm looking for. Those are bigger than what I'm looking for. You can throw elements away. But not so with sorting. So with merge sort, we're going to have the list log n times. And that's as many times as we can divide something in half. But every time we have the list, there's this key step of merging. Well, suppose I have the list down to size 2. How many steps are involved in merging a list of size 2? It's like 2 or, it's like 2 or 3, right? You have to compare them. Then you need to move one, then move the other. So it feels like it's 2 or 3, give or take. But it's some linear factor of the number of buckets. Same here. How about when we had 2 halves like this? These were sorted and these were sorted. Then we had to merge them. How many steps did it take to merge these things? Well, you can actually simplify this logically. If these plastic bins were at this location a moment ago, and this half was sorted, this half was sorted, now we needed to merge the 2 halves. Well, how many steps does this take? Well, you can just kind of infer. Well, this guy ultimately has to move into his location. This guy has to move into his location. This guy has to be merged into his location, and this guy into his. So it's again 4. Maybe give or take if it's actually maybe it's 8, right? Maybe you need to compare them and then move it around, but it's still linear because there's only 4 things you need to merge in total. So it feels like every time we have the list, we have to do something as many as n times for the merging process. And so in the end, merge sort, and we'll see this in just a moment, merge sort is what we'll say is in big O of n times log n. So this refers to the merging. At the end of the day, you've got to merge n elements. But this refers to the number of times you're going to have the list again and again and again. So you get n log n. Now, again, just quick sanity check without dwelling on what a logarithm even is necessarily. Which of these is smaller, n or log n? So log n is smaller. So then why is merge sort so much faster than bubble sort or selection sort? Well, those things are n squared or n times n. This is the same. This is bigger. It's because this second factor is bigger than this that you actually get that n squared feel, that slowness to the algorithm. Well, let's just see this another way rather than just based on buckets. We can express this actually